So in this video I'm going to go through the derivations of optical depth and mean free path. This is based on section 5.4 of Deriving and Peterson, where it's given its formal name. This is a type of radiative transfer. So we're considering photons passing through a small chunk of some kind of gas which contains atoms. So let's say we have a beam of light of intensity I incident on a small chunk of this gas, which is going to have a cross-sectional area A and a depth dx, a small depth. Assuming there's no light source in that chunk of gas, what comes out the other side will be I plus di, where of course this di is going to be negative. We're losing light as it passes through this gas because photons are going to interact with particles in it. Let's imagine that the volume includes only a single particle, and that particle has a cross-section which we'll label as sigma. This isn't the physical size of the particle, of course, right? This has to do with all of the kind of electromagnetic interactions and all kinds of subatomic or atomic physics to do with the particle. And these sigmas are known for a variety of different particles. If we just have one particle in this chunk of gas, and sigma says the area of the gas that it covers, so the fraction of the area that is covered by this particle is sigma over A. That's the fraction of photons that are going to get absorbed as they pass through this small chunk of gas. So we can write down that the fraction of the light that's absorbed, that's going to be di over I, is just equal to the cross section over A. And since we know that the light is going down, we know this is negative, so we know that this is going to be minus sigma over A. Okay, so now to move on, we need to consider not just a single particle, but a number of particles that are going to have a number density little n. So say particles have a number density little n. Then in our little chunk of gas, we're going to have a number of particles equal to big N, which is the number density times the volume. And the volume, of course, is the area times the length. That's the total number of particles in our little chunk of gas. So now, as long as those don't overlap, the amount of light, or the fraction of the light that's getting absorbed, di over I, is equal to minus the number of particles times their cross-sectional area divided by the total area. So again, that's the fraction of this little area element that's covered by particles, or covered by the cross-sections of the particles. And if we put in our equation for n, which you remember was n, little n, and then the volume, which was dx times a, so we've got minus little n, number density times dx times a times sigma divided by a, we end up with our final result, which is that the fraction of the light that's absorbed is the number density of particles times the cross-sectional area of a single particle times the length of the element. So now if we take the limit where dx tends to 0, we can turn this into a differential equation, of course, right? So our equation becomes di over I is equal to minus n sigma dx. If we integrate both sides, we can solve this to give us natural log of I is equal to minus n sigma x plus our integration constant. And now if we just say that the intensity is equal to I0 at x equals 0, we can solve for the integration constant and come up with a final result, which is that intensity as a function of x is our integration constant, the intensity at x equals 0, times the exponential of minus n sigma x. And that's the equation of radiative transfer through a gas of particles. Now we use a number of other definitions that I just want to mention here before we end. So let's write down this equation again. I is I naught e to the minus n sigma x. We define the optical depth, tau, to be equal to minus n sigma x. Right? And if tau is much, much bigger than 1, if you look at that equation, no light's getting through. This is optically thick or opaque. If tau is much smaller than 1. This is optically thin. Most photons go through. Now the average distance a photon will go to through this material is tau equals 1, an optical depth of 1. And so we also define that to be the mean free path. Mean free path. And if you look at that, the units of 1 over n sigma have to be the same as units of distance. So the mean free path is L equal to 1 over n sigma, and that's the average distance a photon travels through a material, and when it's travelled that distance, it's travelled to an optical depth of 1.